Hi, everybody. Welcome to this video, which is going to be about proper value equivalence. Proper value equivalence is an extension of an already existing concept in reinforcement learning called value equivalence. We're going to be discussing both of these topics today. We're going to see what proper value equivalence brings in addition to what we already have given the value equivalence framework. We're going to see how these relate to reinforcement learning as a whole. And we're going to see the definition associated with these two kinds of value equivalences. So let's jump into it. The first thing we want to look at is an overall aim that we would like to achieve in reinforcement learning, specifically in model-based reinforcement learning. In model-based reinforcement learning, you could imagine a scenario like we have in the figure here, where we have some sort of vehicle that we want to control. The vehicle needs to drive down the street and it needs to avoid, for example, pedestrians and crashing into various objects. And one way you could model this in a model-based reinforcement learning setting would be to model all the details of the environment. That would be a very accurate representation. So, for example, if you have a video game, you would take all the renderings into account. If you had an actual self-driving vehicle, you would take all the camera input into account. While that is very accurate, it would require a lot of computational work to represent that state, and then also a lot of work to be able to train a model using all that complexity. What would be better and easier for some sort of algorithm to make use of would be something like what we see to the right here. It contains all of the crucial information that we would need for planning. So we have all the pedestrians, for example, in place. We have all the buildings that we want to avoid, but we've cut out and abstracted away some of the details of these representations. So we don't have the signs, for example, that you can see on the buildings to the left, and some of the unnecessary complexity of this model has been removed. Now, the output of these would most likely be the same. We would get the same sort of policy for our agent, regardless of if we trained it with the first or the second representation. But the second one is obviously preferable. And value equivalence and proper value equivalence are both concepts that we can use to get to this second representation. So they are tools that we can make use of in order to simplify our environment. To make it very concrete what these sort of concepts are, we're going to look at a definition next. So the definition of what's called the order K value equivalent class can be seen in green or blue here. It is a class of models that has two input parameters, pi and v. These are two spaces of policies and value functions. We're going to digest this expression bit by bit. So if we start on the left-hand side here, we can see small m belonging to big M. Big M is the set of models that we are allowed to consider, and small m is the particular model that we're focused on now. And what we mean when we say model is illustrated at the bottom of this slide. So we can see on the left-hand side here that we would have some sort of state at a given point in time and some sort of action that we take, represented here by the controller. Then we would have a model, and the model is intended to model how the environment develops as a consequence of our state and action. So what we get as an output from our model would be the state representation here, one time step later. So if you look closely, you can see that the ball here has actually moved a bit closer to the racket at the bottom of the screen, and that represents what the model would do. It also gives us a score because part of our state representation here would be essentially the points that we have. So by the model, we mean these two concepts. If we look at the second part of this expression here, we can see this T, which stands for the Bellman operator. We're going to look at that in more detail in the next slide here. So what the Bellman operator represents, if you're unfamiliar, is essentially the value of a state. It's a way of bootstrapping the value of a state, taking into account information of upcoming states. And the way this is evaluated, so the way this Bellman operator applied to a function v is evaluated, is the expectation over the actions chosen according to our policy. So the policy is how we act. The actions are what we choose to do in a given state, provided that we have or follow that policy. S prime is the next state, and P of SA is the probability distribution of our next state given our current state S and our current action A. So you might be in a probabilistic environment where the next state that you get is not exactly determined by the state in action, but there might be some randomness involved here. So this is some sort of distribution. And we take the expectation over this for, this value in brackets here. So that is the reward, the immediate reward you would get by taking action A from state S, and then a discount factor gamma times the value function at the next state S prime that we would go to as a consequence of then performing action A. And so this is the definition. And what you can see is we take the current reward and then discount the future value of the next state that we will get to. So if you have a reward in the next state, that will in time get propagated backwards. And that's sort of a very fundamental aspect of reinforcement learning. If we look at V here, then that would be the value function, as we said. And then what's very important to note with this expression is that the Bellman operator depends implicitly on the model that we choose for the environment. And that's where this really connects to value equivalence. So if you look at the expression here, for example, S prime equals probability distribution of S and A. This probability distribution depends on our environment. And specifically, if we're using model-based reinforcement learning, it would depend on the model that we've selected for the environment. Now, if our model changes, which it naturally will do if we simplify the environment, then this probability distribution will also change. So we need to, when we simplify the environment, simplify it in such a way that this quantity is to some extent robust, right? That seems like a reasonable criteria for us to be able to simplify something without removing critical information for the sake of planning. And one thing that we can additionally note is that if we repeatedly apply this Bellman operator multiple times to our function v, that's denoted here by raising the Bellman operator to the power n. So as we let n tend to infinity in this expression, we will get the value function, so the actual value function given our policy pi. So that is a convergence criteria that we have for the standard Bellman operator. Now that we know what the Bellman operator is, let's look again at the definition that we highlighted in the previous slide. So we have the definition here, and we said that we have a model M tilde in the set of models big M. And what we require is that K applications of the Bellman operator with a tilde on it is going to be the same as K applications of the standard Bellman operator given V. Now, the differentiation between these two, so the difference between the tilde and T, is that this Bellman operator is the Bellman operator associated with the actual environment. So that is, in some sense, the true Bellman operator that you would have if you took all the complexities of the environment into account. What we say now is that after K applications of this perfect Bellman operator, or the Bellman operator contingent on the perfect model, that will give us the same answer as applying the standard, or well, the simplified Bellman operator, or the Bellman operator associated with the simplified model K times. If these two are equal for all policies pi in the set of policies that we consider, and all value functions in the set of value functions we consider, then we call this a order K value equivalent class. That is the definition. And the classical value equivalent definition was for K equals 1. So that would simplify this expression. It would turn it into just T pi V here. So just one single Bellman operator. And we would require that those are equivalent. Now, the extension that we're considering here, which will ultimately take us to proper value equivalence, is with this K. So we allow for an adjustment of where these two actually need to coincide. So you could have differences during, let's assume K is 3. You could have differences for the first two operations of the Bellman operator, but on the third one, they need to converge to the same expectation value. So that's the value equivalent class. And we want to use this concept now in order to see what kinds of state representations might give us value equivalent models, and which ones would be associated with non-value equivalent models. So in order to give an example here, we have some original model to the left. We can see that all of the sort of details in the background are contained within this state representation, which we already agreed is non-optimal. And to give a simple example of something that would be non-value equivalent, we can investigate the model here at the middle. We can see that here we simply cut out half of, well, of the screen that we would use for this video game. And this will definitely not give us the same value equivalent concept that we've been discussing up to this point. So imagine, for example, a car would come facing you on the left side of the road. You would normally plan that differently depending on which of these models you have, because in one of them you wouldn't necessarily see the vehicle approaching you. So for obvious reasons, the second one here will not give essentially value equivalence. The third one, however, might. So we have here a state representation where we cut out all of the surrounding aspects of the environment that are non-crucial for planning. So we can still see the vehicle that we have ahead of us. We can see where the road begins and ends. And all of those are necessary aspects to consider how we want to maneuver our vehicle. But all the details besides that have been removed, which would ultimately speed up computation. So this is an example, and it gives an illustration of what might be considered value equivalent and what would not be considered value equivalent. Okay, we're going to get even more specific now and talk about the case where k equals 1. So this is the old notion of value equivalence, where k equals 1, and we require that the Bellman operator with a single application is the same for the simplified model and for the full model, right? There was a problem associated with this, which is what this new proper value equivalence topic actually addresses. And that has to do with when we get more specific in terms of our requirements, or when we get more stringent on our requirements. So we have something of the form here, M1 of pi v, where pi and v are the states or the sets of policies and value functions that we require that the two models be equivalent for. So you can imagine pi just being a small, simple policy saying, let's say, if we always turn left, we want the models to behave the same or to give us the same sort of answers. But you can also expand this concept, and that's why we have a set of policies here, not just one policy as input to this set. You could have a policy where you say we only turn left. You could have a policy that says you only turn right, and you want it to act the same for both of those. And you can expand this to include more and more policies. The more policies you include, the more stringent you become in your requirements for the model you use. So it's trickier to build a model that behaves very similarly in all different scenarios of acting compared to something that only needs to behave the same if you always turn left, for example. So it puts more constraints on what models will be applicable. And therefore, the set of permissible models will decrease as this set of policies, pi, and the set of value functions, big V, expand. What has been shown by the people at DeepMind is that if we let these expand to the most wide sets that you could possibly have, so the bolded pi and v, as we indicate those here, we actually get that it either contains the full environment, that is the fully specified environment with all its detail, or it's going to be empty, meaning that there is no permissible model like that. So that is a limit criteria, which at first may seem kind of good because it means we converge to the model that we're looking for. But actually, this is somewhat a curse in disguise. The problem is if we include more and more policies, we're going to require having a model that at some point converges with the full complexity of the original model. But we know that there might be information in that model that is not necessary for planning. So we're only interested in planning, not the other stuff. But even though we are only interested in planning, this sort of k equals 1 version of value equivalence will not give us some flexibility in terms of the models that we can pick. So it is really something we want to get around, and that's what we're getting around with proper value equivalence. What should be noted, and what is sort of a motivation for proper value equivalence, is the above limit is not necessarily existing when k is bigger than 1. So if you give some slack in terms of what time step the Bellman operators need to coincide between the simplified model and the actual model, then you don't necessarily have the criteria that you converge to the single model in the limit. This brings us to proper value equivalence. We get to proper value equivalence as k tends to infinity. So it's the limit where we give or where we require that an infinite number of Bellman operators given the simplified model produces the same result as an infinite number of Bellman operators given the perfect model on our value function. The first thing we should note from the definition here, where the limit of k goes to infinity, is that instead of having an infinite number of Bellman operators onto the original value function that we specified, we simply see the equality between the value function under policy pi for tilde, that is the simplified model, should be equal to the value function under the policy pi for the actual model. And the reason why we don't have an infinite number of Bellman operators included in the definition here is that when we apply the Bellman operator to our value function an infinite number of times, that converges, and we discussed this before, to the value function given policy pi. That is a property of the Bellman operator, and therefore we don't need to write out the actual usage of this Bellman operator in the definition here. The second thing that this actually means is that the set of models contained in this proper value equivalence set is independent of the set of value functions that we consider, because for the same, or the reason for that is the exact same reason that we just described. If we start with any value function, regardless of which one we start with, that will per definition converge to the true value function given the policy and the model that we have in the limit. And since we're only considering the limit now, it doesn't matter what our starting value function is. So the set of value functions we consider doesn't matter for the definition, and it will only be a function of the policy that we consider. Okay, so if the set of policies increase, just like before, this would tend to decrease the set of applicable models that we have. We have a schematic representation of the different kinds of value equivalence sets here. And the thing we would like to highlight is that the proper value equivalence set is the intersect between all of these different sets. So it's in some sense the largest one that you can get, because we only require that in the limit, as we apply these Bellman operators, they will be the same. Okay. And we can therefore also define this as the intersection between all the individual value functions that we have. And by far, the most important finding of this sort of new way of looking at value equivalence is that in the limit now, we don't have convergence to a single value. And that's really the reason why we're using this new definition, because it's slightly more complex perhaps than the previous one, but it gives us the benefit of not having to trade off between complexity in the model and then also results that we get in terms of planning. Because if you have an order 1 value equivalence definition, you would always need to have a trade-off between the two, because in the limit, like you cannot take the limit without converging to the full model, and that if you do, you haven't actually simplified the problem. So the order 1 value equivalence framework requires you to do a trade-off, and we can circumvent this with the new definition that we've just described. So to summarize the results that we have some comparisons of, or some statements of why this M infinity is actually useful. So unlike value equivalence, the class of proper value equivalence does not collapse in the policy function limit. That is essentially what we described just before. Even if all value functions are used, we generally end up with multiple models. So that is tied to the previous one. And what this means is that some of these models might be simpler than others to represent. And so if you have a set of models that are permissible, the smart thing to do would be to take the simple one. And so if you think about what we've been able to achieve now, we've been able to take some sort of concept that is, or some sort of model that is very complex, get a set of applicable models that are less complex, and then we can choose the one that's most beneficial for the aims that we have. And that's really the strength here. And that's what's going to be used, hopefully, going forward in many reinforcement learning applications. So this is it. This is where we're going to conclude. Thank you very much for watching, and I look forward to seeing you in the next video. Goodbye.